All right. Hello. So when I think about folks building new robots or smart devices today, I'm reminded of the adage about the last 20% of the project taking more than 80% of the time. You can kind of liken it to the Pareto principle. But that last 20% usually includes adding authentication or authorization to those machines, which can lead to refactoring the initial assumptions that led to maybe thinking they had access to that information or other systems that won't always be true. Putting the business logic around hardware is more than just slapping a cloud portal in front of a dashboard or a control panel. It can be so intimidating for these companies that they never feel comfortable connecting the devices, falling back to tethered controllers, and missing out on the benefits of distributed data capture, over-the-air updates, and coordinating fleets and other automation opportunities. But when they do so poorly, then consequences are soon to follow. Hi, I'm Nick. I'm a senior developer advocate at Viam, where I help people build and bring their hardware projects to life. When I'm not tinkering on robots, I like to go on long bike rides or climb at my local gym, unless there's an active project to fix up my house, which there nearly always is. My talk proposal included the line, "Don't let your toaster order unauthorized parts." So this is the generated image off of that. Hope you enjoy it. We'll cover quite a bit in this presentation, from an overview of the landscape of devices that I'm talking about, also to the fundamentals around authenticating those devices. We'll jump into some example architectures and authorization strategies that will follow with real-world examples to solidify our understanding of those concepts. And we'll conclude with some final thoughts and takeaways. So first, let's get a sense of the scale I'm talking about. There is no end in sight for how many more things will come online each year. This includes cars, glasses, household appliances, and more. Projected 30 plus billion connected devices will come online within this decade. But there's even more important than the sheer numbers is the diversity of them. Just like I said, we're talking about everything from industrial robots to autonomous vehicles, smart refrigerators, and yes, maybe even internet connected toasters. Each device category brings its own set of authentication challenges, hardware constraints, and security models. And the complexity increases exponentially when these devices need to work together across manufacturers and protocols. This expanding attack surface makes proper authentication not just important, but essential. Because without it, the risk range from personal security violations to critical infrastructure compromising. These aren't just theoretical concerns. We've seen real-world examples of IoT security gone wrong. Maybe you heard about this example with Eufy or Wise, where they leaked camera footage after an AWS outage caused issues with their authorization infrastructure. Maybe you remember the Mirai botnet that took down major websites by harnessing the power of compromised cameras and routers, or other smart home devices that have been hijacked to harass people. The consequences of poor authentication in connected devices extend beyond the digital realm into physical safety. When your device can move things in the physical world or control critical systems, security takes on a whole new dimension of importance. And yet, many devices still ship with default passwords, unencrypted communication, or no meaningful authentication at all. We need to do better. Given this is a customer identity and access management conference, I expect that most of you know the difference between authentication, Auth-N, or authorization, Auth-Z. But let's go over it anyway from the perspective of a device as the customer. Authentication is proving identity, right? And then authorization comes next to confirm access. A device is able to confirm it is a known member of some registered database, or a person is able to identify themselves with the device. For authorization, does that registered device have access to store data, read data, take action in a system? Can a person make changes to a device's settings, install new software, or command the device? Will that always be true? These concepts provide boundaries around who, what, and where, all that enable smart machines to operate independently or not. As I keep mentioning, we're not just talking about your smart speaker light bulbs at your home. It's millions upon millions of cameras, industrial machines, and roaming robots that are ingrained in our world. They vary in computational resources and internet access, both in bandwidth and stability. There's also a variety of physical environments in which they live, from temperature controlled data centers to harsh outdoor conditions in farm fields, the ocean, or even space. Given these environments that most people want to stay out of, they need to survive for longer lifespans than typical consumer devices. Also, how do you handle unauthorized physical access to these devices? Let's cover some core authentication principles. Each device needs a unique, verifiable identity that can't be easily spoofed or compromised. Credentials used by these devices and people accessing them need secure ways to be provisioned, stored, updated, and revoked. Devices should be able to act by the principle of least privilege. What is the minimum amount of authorization required to complete their function? And it's not if, but when something happens to any system. So proper monitoring and alerting of compromising behavior will ensure any breach of security has as little negative impact as possible. So provided these principles, how can we apply them to specific architectures for our authenticating systems? At a high level, we can categorize these into cloud connected models where devices authenticate through central cloud services and peer to peer models where devices authenticate directly with each other. Many real world systems use hybrid approaches, combining elements of both, and the right choice depends on your specific use case, device, and deployment environment. Let's explore each more in detail. By providing a central cloud service for interacting between devices and users, it's easier to update security policies, monitor device behavior, and keep an eye on the entire fleet from a single place. But that can also be the single point of failure in cases of internet instability or time sensitive operations. Within cloud connected architectures, there are several common authentication methods. You have the API key based approaches that are the simplest. Devices can use pre-assigned keys to authenticate with cloud services. OAuth flows can be adapted for devices to allow for more flexible permissions and token revocation. JOTs or JWTs and other token-based workflows can provide time-limited access similar to OAuth without the constant cloud communication. And certificates for public key infrastructure or PKI are more complex but have stronger verification guarantees and work with intermittent connectivity as well. Each of these can help provision devices that are sent into the field or prepared before deployment. Now let's look at peer-to-peer authentication, where devices authenticate directly with each other rather than that cloud intermediary. This is very useful for situations without reliable internet connectivity, ultra low latency requirements, or even local autonomy that's critical in places such as air gap facilities. To enable these benefits, you need to figure out how to distribute, manage those credentials to a fleet, establish initial trust without a central authority, and keep it all consistent across all of your devices. For peer-to-peer authentication, you have several methods available. mTLS, mutual TLS allow devices to authenticate with digital certificates with each other. Secure hardware keys can be embedded in devices during that device provisioning or flashing that can reduce vulnerability to physical tampering, but are harder to revoke. Zero knowledge proofs can allow devices to verify their identity without exposing any sensitive credentials. This mTLS establishment diagram from ngrok is very helpful. Just imagine the server side is replaced by another device on the same network or proximity of the client. So now we've authenticated ourselves or your device, you'll need to maintain authorization as well. Whether using cloud or peer-to-peer authentication, role-based access controls, RBAC, is a powerful implementation strategy for managing device permissions. In the IoT context, RBAC means defining clear roles for different types of devices and limiting their capabilities accordingly. For example, Admin or owner devices might have full system configuration rights. Operators might control physical operations of devices, but not change any system settings. Read-only sensor devices could only report data without any actuation or control. And then gateway devices can provide limited access to the internet for sensors and operators, but have no real authority over them. By assigning each device to an appropriate role, you'll create a nice boundary that limits the damage of any single device if it's compromised. Provisioning or setting up a device for the first time is crucial for any authentication or authorization architecture. A customer, administrator, or even another device needs to establish the initial identity for the new device, typically through physical access or proximity like a shared local network or a hotspot like we're seeing here. As long as the provisioner has access to do so, they can authorize the credentials, whether it's keys, tokens, or certificates. Those credentials can be assigned to the least amount of privileges possible based on the device's role in the overall system. Finally, the new device should start its monitoring either internally, peer-based, or cloud-based to detect bad actors or other negative behavior. As we can see here, this device is getting set up through a mobile application, being assigned a Wi-Fi network, and then starting to connect to the cloud or even directly to this device to start seeing detail from sensors and other peripherals connected to it. Speaking of bad actors, as I mentioned, it's not if but when something goes wrong. Then how do you handle it? This is where credential rotation and secure updates need to be in place. Just documenting these procedures is a good first step, but then automating any of them, whether it's the rotation or certificate renewals or security patches, will make your product even stronger. In this case, we can see you can grant access, but also limit it at any time and revoke it completely. Using everything we've covered so far, we can explore 2 example scenarios for securing a fleet of devices. So in the example of a smart factory, robots in an industrial space, such as a manufacturing facility, can include automated arms, mobile bases that are performing various assembly and transport tasks within that line. You could implement this as a hybrid architecture. Robots are authenticated to a central cloud service during initial setup and management of operations. They authenticate with each other to pair on time-sensitive tasks using something like mTLS. Each robot can store its identity and those mTLS credentials on a secure harbor device embedded on the machine. And then all communication between the robots and the cloud are end-to-end encrypted. Some things to keep in mind for this scenario: uptime is key. So taking all of the robots offline for updates isn't practical, so you want to keep operations running as smoothly as possible. You'd want to implement a rolling update process that only reduces capacity for a fraction of the line at a time, as well as provide early warnings for any broken updates that could affect the entire fleet. For this next one, we can take a look at a more personal environment, the home. Unlike the factory example, devices here come from all different vendors and use competing or overlapping protocols to communicate. Plus, there's no assumption of technical knowledge by the people setting them up. This will lead to more cloud-based authentication since devices communicate in conflicting ways with each other. OAuth provides a familiar authentication flow for users with a solid foundation in security. Privacy considerations are very important while balancing the ease of setup and use over time. To wrap up, here are some key takeaways that I hope you'll continue to think about after this presentation. Authentication is not just a feature of connected devices. It's critical infrastructure that demands careful design and implementation. Plan for the entire life cycle of the device, from secure onboarding to credential rotation to eventual decommissioning. Choose the architecture that fits your constraints the best. Find the balance of secure defaults and usability, The most secure system in the world is useless if it's far too complex to actually use. And that's what I have for you today. If you want to learn more about what Viam does in providing both authentication and management of devices, you can sign up for our newsletter. You can also check out our documentation, join our community Discord, or even build your first robot with our hands-on code labs. You can follow Viam at Viam Robotics on socials, or me at Hipster Brown, or just Nick Hehr on LinkedIn. Thank you very much.